Hi everyone, welcome to Chapter 5. Chapter 5 is all about polynomials. So first we want to start with some terms, make sure we understand what we're talking about. Polynomials could be just one term, a monomial, or a sum of many monomials. And these terms have degrees. And the degree of the term is the exponent of the variable. That gives you the degree. So you can have a degree of a polynomial is the greatest degree among all the different terms. I'm going to put a chart on the board, it's also in your book, that shows the types of degrees of polynomials, and then we're going to learn how to put them in standard form, how to determine what degree they are, and how to classify what type of polynomial they are. You want to know what you're dealing with. Okay, on the board I've copied the chart that is in your textbook that shows the different types of polynomials that you can have. When they are in standard form, you always write them, and these are all, we're looking at polynomials in terms of x, where we just have the one variable x, but you write the terms in order of degree, the highest degree first, and then descending. So if we have a degree of 0, that is called a constant. It would be just a number. The exponent is 0. We have no variable at all. Okay, this example has just one term in it. It's 5. And when we have a polynomial of one term, it's called a monomial, because mono means one. Our next example is a degree of 1. So a degree of 1 is called a linear, because if we graphed it, it would graph a line. If we graphed this, it would just be a point, wouldn't it? This creates a line, so it's linear. And an example would be x plus 4. So y equals x plus 4, or f of x is x plus 4. That's an example of a linear equation. Notice this is a degree of 1 because the exponent of x is 1. This has two terms, x and 4. So it's two terms. When you have a polynomial with two terms, it's called a binomial, bi for 2. If we have a degree of 2, its degree name, we call that a quadratic. It's a quadratic because our highest degree is 2. An example, 4x squared. This example has only... If we have a degree of 2, so the highest degree is the x squared, that's called a quadratic. So the example of my quadratic here is 4x squared. That only has one term, so it is another monomial. This is the name determined by how many terms it has. This is its name by its degree. So you can classify it two ways. You can classify it by degree and by the number of terms. Often you will be asked to give me both, so be careful. All right, if our highest degree is 3, it's a third degree polynomial. Those are called cubics, and that means our highest exponent is a 3. Here's an example of a cubic polynomial. This one has 1, 2, 3 terms. When it has 3 terms, we call it a trinomial. Makes sense. All of this is pretty logical. Fourth degree, that means our highest exponent is 4. We call that a quartic. Quar for a quarter. 1/4 is a quarter, right? Quartic. Here's an example of a quartic polynomial, 2x to the 4th plus 5x squared. This has 2 terms, so it is another binomial. I just wrote the prefix. And then 5th degree. A 5th degree is called a quintic. Here's an example of a 5th degree polynomial. This one has 1, 2, 3, 4 terms. When you have 4 terms or above, then as far as number of terms, you can just say it's a polynomial of 4 terms. You don't have a special name for anything above trinomial. All right, so that gives you how to classify by the degree and by the number of terms and examples of what these look like. A polynomial is in standard form when the exponents, when the terms are written in with the exponents in descending order. So you write the highest degree first. This one is not in standard form. The x squared should be before the x. So 9x squared should be first, followed by, so x to the power of 2, followed by x to the power of 1, followed by x to the power of 0. Now it's in standard form. And if you were asked to classify it by degree, this would be a quadratic because it has a degree of 2. It has 3 terms, so this is a quadratic trinomial. Here's another polynomial. It looks like we have 5 terms, but if you look carefully, you can see there are some like terms that we can combine. Definitely do that. So as you write it in standard form, make sure, can you simplify it at all? Notice there are 2 x squareds that we can put together. So the first term would be our greatest degree, x to the 4th. Combine our 2x squareds, negative 6 and 10 is positive 4x squared. Then we have single x, positive 4x, followed by negative 12. Now it's in standard form. So if we were to classify it, this is a 4th degree polynomial, so it is a quartic, and it is 4 terms. So this is a quartic polynomial of 4 terms. If your degree is even, so it's a 2 a squared, or it's a 4, or it is a 6, so it's a quadratic, or it's a quartic, or it's a 6th degree polynomial, that means that the ends of your graph, if you put this on a graph, are going to go in the same direction. We already have graphed quadratics, so we know that quadratics form a parabola, right? The 2 ends go in the same direction. If my coefficient is positive, we know the quadratic opens up, and just like this. If my coefficient is negative, then the 2 ends go down. That's the end behavior. So if this is positive and even, the end behavior is up and up. If this is 4th degree and this is positive, up and up. If this is 6th degree and this is positive, up and up. If they are negative, down, down. Do you see? Just like we learned in quadratic, any even degree works the same way. Now, the maximum number of turning points is 1 less than the degree. So for instance, when we did quadratics, it just had 1 turning point. That was the vertex, and we found that vertex and graphed that turning point and then drew our parabola. If it is a 4th degree, it could have 3 turning points, which sounds kind of crazy, but it could. So it could go, start here, 1, 2, 3, right? 1, 2, 3 turning points, kind of crazy. And if it's 6th degree, it could have 5 turning points. That's the maximum. Some of these are so small it doesn't look like it. You could have a 4th degree that looks kind of like that. Whoops, more like that. But anyway, that's how you do the number of turning points and the end behavior when these are even. Now let's look at what a polynomial will look like if its degree is odd. So if it's linear with a single x, or if it's cubic, or if it's quintic, or if it's 7th degree, or whatever, the 2 directions will not be like a parabola. They will not go in the same direction. They will be in opposite directions, just like a line. If you really think about these graphs, you're thinking about eternity and infinity for the ends. What we focus on in the graphs is the middle, all the squiggly stuff that goes in the middle. But basically, for all eternity, they basically just look like lines with some squigglies in the middle. That's what these things look like. This is just a line. If this is positive, it's a line that goes up from left to right. It has a positive slope. So the left end behavior is down, the right end behavior is up. The book will call it down, up. I just say, think of a linear line, think of linear, a line with a positive slope. If this is negative, then it's going to be a line with a negative slope. So the left end will go up, the right end will go down. The same is true if it's a third degree or a fifth degree. They will also be linear. So if the term is positive, it'll be, for all eternity, a line with a positive slope, down, up. Or if it's negative, same thing, a line with a negative slope, up, down, left to right. You're always reading left to right. Now this means we can have some turns in it. If this means 1 less than 1 is 0, there are no turns at all, that's a straight line. 1 less than 3 is 2, so I can have 2 turns. In this, I could have 1 turn, 2 turns, there we go, if it's cubic. If it's quartic, I could have as many as 4 turns. Crazy. That's the maximum number of turns, T-U-R-N-S, turns that I could have. All right, so let's see, we are given this polynomial function. I should have written y equals this. And you were asked, what's the end behavior? All you need to look at is the first term. The rest does not matter at all. Look at the degree. It's a third degree. That's an odd number. So it's going to look like a line. Now look at the coefficient. It's positive. That means it's going to look like a line with a positive slope. So you will describe the end behavior as down, up. That's what they're going to look for on the computer. A positive slope left to right. Here's another polynomial. This one has 4 terms. This is a quartic. It looks really, really involved, but if all they ask you is the end behavior, you can ignore everything else but this first term. Look at the degree. It's a 4th degree. That means its basic shape is going to be a parabola. Its basic shape is a parabola. It just could have some wiggles, but it's a parabola. Either opening up or opening down. Look at the leading coefficient, it's negative. So that tells you its basic overall shape is a parabola opening downward. So the end behavior is down, down. And the maximum number of turning points it would have would be 3. You will be asked to graph some of these. If you have a graphing calculator, that's fine, but who cares? You want to know how to graph it by hand yourself. So when you do this, look at that end behavior first of all. So let's just look at this simple, relatively simple, y equals 1/2 of x cubed, this simple cubic. Notice it is an odd, so it's going to look like a line. 1/2 is positive, so it's going to look like a line with a positive slope. What I would suggest is build a table and focus on the area around 0. You won't need a lot of points, but just a few around 0. So let me build a table, show you what I mean. Absolutely, without a doubt, when you build a table, you need to go on both sides of 0, or you're not going to get the whole shape. Your end behavior has to match what you're expecting. So I picked just a few points on either side of 0. I'm going to plug those in. So -2 cubed is -8, and half of -8 is -4. I'm going to go ahead and do the rest of these. Okay, I've determined my points. Now I'm going ahead and I'm going to graph them on the graph. And there's my graph. Notice it does look like a line going in a positive direction. Here's where the little turns were. Remember I said this is the maximum number of turns. So maybe you wouldn't say that there's 2 turns. Maybe I don't know how you would describe that actually, but this is what the graph would look like. That's how you do it. Here's another cubic that you've been asked to graph, not in standard form, so be careful of that. But still look at the greatest degree to determine end behavior. This is what you look at. Don't look at this because in standard form, this would be first. It's odd, so it's going to look like a line, but it's negative, so it's going to be a line that should start up and go down, a negative slope. So let's build a table and plot some points. Notice I picked the same points right around 0. All right, I plugged each of these in one at a time, and this is what I got came out. So my next step is thinking, good grief, what in the world is this gonna look like? So plot those points. If you look at these points, they look like they're all over the map. This is where students make their biggest mistake. When you connect from point to point, always go along the x-axis from left to right. Remember, we're expecting a line with a negative slope. And our first point here at -2 is up here. Our next point at -1 is down here. So, whoops, not very straight, sorry. Then I'm going to turn and notice here's my overall line, and I have 2 turns. These are pretty significant turns. That's the maximum number of terms, like turns with an N, turns I can have with a cubic, and there's the overall shape of that graph. So this 3x made quite a difference in the way this graph looked. Sometimes you are only given a table of information and you don't know what kind of polynomial that would fit this data. There is a way to take the data and determine what degree polynomial would fit this. And we're going to use differences in order to do that. So first of all, notice our x's are in order, not skipping any numbers, just integers. Here I have -3 up to 3. When there's no gaps and my inputs change by 1, then I can use differences. And what I do is I look at the outputs, my y's, and I find the differences between them, go in the same direction. So in this case, I could go -7 minus a -1, which would be -6. Please be careful you're subtracting. So these two would be -6. Then I go -3 minus a -7, that's 4. 5 minus a -3, 8. 11 minus 5, 6. 9 minus 11, -2. -7 minus 9, -16. And you may be thinking at this point, what is she doing? Notice I have found the differences one time, and these numbers are not the same. So I'm going to do it again. 4 minus a -6, that's 10. 8 minus 4, that's 4. 6 minus 8, -2. -2 minus 6, -8. -16 minus a -2, -12. At any point you could make mistakes, so be careful when you're doing this. So now I found the difference twice. Still, my numbers are not the same, so I do it again. Before I do it again, I made a mistake. -16 minus a -2, -14. Candy, where were you? Oh no. All right, do it again. 4 minus 10, -6. -2 minus 4, -6. 8 minus -2, -6. -14 minus -8, -6. Finally, I get all the same number. So the first differences didn't give me a result. The second differences didn't give me the same result, but the third differences did. This data fits a third degree polynomial. Third degree. So that means that it would fit an equation that looks like this. Obviously, I don't know what my coefficients are, and I don't even know if it would have 4 different terms. Some of these could be 0, but I would have x cubed is my leading term. It is third degree because my third difference were all the same. It's so cool. If the first difference is all the same, it's linear. If the second difference is all the same, it's a second degree quadratic, etc. So this method is pretty cool, the way it works. Your lesson check for this section is to take this table of information and tell me what degree polynomial fits this data. So you're going to have to go through that process with these y's. If you have trouble seeing it on my video or copying it down, this is in your textbook. It is on page 284. It's the got it question number 4. The answer's not there, but these numbers are. And then too, if I made a mistake copying them down, check it out on that page and see if you can figure out what degree polynomial this would be. And that's your lesson check. That was quite a bit of information. How to classify polynomials, how to put them in standard form, how to determine their end behavior and the maximum number of turning points, how to graph them, and then how to determine what degree polynomial would fit data. Quite a bit. So hopefully you took good notes and you can work through that, and these will slowly, hopefully with time, become second nature. That's it for now. I'll talk to you guys later. Bye.